In this class, I shall be talking more about the equilibrium constant Kc, where you know that this equilibrium constant Kc is related to the chemical equilibrium. That is, whenever an chemical equation or a chemical reaction is in equilibrium, then the ratio of the molar concentration of the products to the molar concentration of the reactants is a constant, and that constant is called equilibrium constant Kc. So first, let me tell you about the features of the equilibrium constant Kc. First feature, the equilibrium constant is applicable only when the concentration of the reactant and the products have attained constant value at the equilibrium state. Second, the value of the equilibrium constant is independent of initial concentration of the reactant and the product. Third, equilibrium constant is temperature dependent. That is, it has one unique value for a particular reaction represented by a balanced chemical equation at a given temperature. Thus, equilibrium constant for the reverse reaction will be equal to the inverse of the equilibrium constant for the forward reaction. Next, let me tell you about the applications of the equilibrium constant Kc. The first application is predicting the extent of the reaction. If the value of Kc is extremely large, that is Kc is greater than 10 raised to 3, then products dominate. For example, H2 plus O2 at 500 Kelvin forming H2O. The value of Kc for this reaction is 2.4 into 10 raised to 47. So, H2O concentration will dominate than the concentration of H2 and O2 at equilibrium. If the value of Kc is extremely small, that is Kc less than 10 raised to minus 3, then under such conditions a reactant dominate. Finally, if the value of Kc is intermediate, that is between 10 raised to minus 3 and 3, then appreciable concentration of both the reactant as well as the product are present at the equilibrium state. Second application, predicting the direction of the reaction. Consider a general reaction A of A plus B of B giving C of C plus D of D. Let us take a ratio QC, where QC is called a reaction quotient, and this QC will be equal to C of C multiplied by D of D divided by A of A multiplied by B of B. Thus, for that reaction, if QC is greater than Kc, then the reverse reaction is dominant. If QC is less than Kc, then the forward reaction is dominant. And finally, if QC is equal to Kc, then the given reaction exists at equilibrium. Consider the following problem where the value of Kc for a reaction 2 of A giving B plus C is 2 into 10 raised to minus 3. If the composition of A and B and C, which is equal, is given as 3 into 10 raised to minus 4, then in which direction will the reaction proceed? Thus, we will first find out the value of Qc, which is equal to concentration of B multiplied by concentration of C divided by concentration of A square. So, we found the value of Qc equal to 1. Since Qc is greater than Kc, the reaction will proceed in the reverse direction. Now, let us study the relationship between Kc and G, where G is Gibbs energy and it is a term in thermodynamics. If the value of G is negative, then the reaction proceeds in the forward direction. However, if the value of G is 0, then the given reaction is said to be at equilibrium. In thermodynamics, you will come across a relation delta G is equal to delta G standard plus RT ln QC. Delta G standard means standard Gibbs energy. We know that at equilibrium the value of delta G is 0 and the value of QC is equal to Kc. So 0 will be equal to delta G standard plus RT ln Kc, or delta G standard will be equal to minus RT ln Kc. To replace ln by log, we have to multiply with 2.303. So finally, the relation between Kc and G will be delta G standard is equal to minus 2.303 RT log Kc.